Good afternoon, everybody. Hope you can hear me. So welcome to my talk about building a .NET cross-platform profiler in an hour. So maybe I cheated a little bit. I'm not going to actually do any live coding to simply take too much. You can't really do that in an hour. You'll see why in a few minutes. But I will show you how to build a simple profiler. So I'm Pavel. I've written a few books, done some other stuff. They're all available online, so please buy them. They make me money, so don't forget to do that later. And how many of you have been to Christoph's talk in the morning? Raise your hands. About mechanisms to see what's going on inside .NET Core processes. Thank you. So not many of you. And so go and watch that session as well when the recordings are out, because you'll see many techniques that allow you to see what's going on in your .NET Core process, whether that's on Windows or on Linux. Now, these tools are great, and I encourage you to use them, but in some cases, you want to dig deeper. You want to gain more information, and the only way to do that is by being within that process that you're trying to understand what's going on in. And so .NET had a long time something called a profiler, which is a DLL that is loaded dynamically into your .NET process, and then you communicate with the CLR to get information about stuff that's going on, such as garbage collection events, or objects being allocated, or threads being created, references being moved, and so on. And so there are many products out there that use this core functionality to create something called a profiler, which gives you a lot of information based on that DLL. So you get a nice UI, you get some analysis, you get information about references, GC roots, and all that nice stuff. And so with .NET Core, we have a similar model. And what I want to do today is show you how we can write a simple profiler, and we can of course extend that later, that can work on any .NET Core process, not just on Windows, but also on Linux, or technically on Mac OS as well, although I don't have one available, so I haven't tested that. And so this talk is about writing native code, so it's going to be just C++. So if you're expecting C# code, you're in the wrong room. You have now 5 seconds to go, because there will be no C# in this talk. So it's going to be native code, because that's the only way a profiler can actually work. Because if I would be able to have .NET code inside my profiler, so what's going on there? So some .NET code will cause maybe a reentrancy to my profiler and will affect the measurements. It's really something that cannot work. And so in the classic .NET, you can use a DLL and register that properly to have it loaded by the process that you're interested in, and we'll discuss that, of course. But in .NET Core, the model is essentially the same. So you can create a DLL in Windows and a shared object file on Linux, and have that, let's call that a module, loaded dynamically into the process that you're interested in. And so this is what the talk is about. How can I use the same source code to build such a profiler and then just use it on Windows or Linux as I need? So let's start with the basics of how profiling works. And so you have your operating system, whatever that operating system may be, and then you have your process that you want to profile. You want to be inside that process to gain all the rich information the CLR has to give you, some of which you can't get in any other way. And so you have your core CLR. The core CLR loads up. That's the first thing that happens from a .NET perspective's point of view. And then the core CLR looks at a bunch of environment variables and then loads up a .NET Core Profiler DLL or module if the settings are appropriate. So they pointed to an appropriate DLL. And that DLL implements a COM object. And I know that people hear the word COM, they typically want to jump out of a window or something like that. Good thing we are kind of no windows here, so it's all good. And I'll discuss that a little bit, so you shouldn't be scared about the word COM here, because it doesn't really mean what you may think it means. And so this DLL loads up and has some communication now with the CLR. And so this DLL, our profiler, can do anything. So I can, for example, log all the stuff that's going on in my process. That would be sort of the minimal thing to do, and this is what we strive for in this short session. But a real profiler can do even more than that. It can use some inter-process communication mechanism to connect to another process that is part of the whole kind of profiler suite that provides maybe in real time some user interface, maybe even the ability to control some of the stuff going on in the process, such as inject calls to GC collect or something, to issue a garbage collection or get information about what's going on in the heap right now. So all this is possible to do in real time, or maybe just gather all the information that we can or need and then just process that offline using whatever logging mechanism we have selected. So this is the general way in which a profiler loads into a .NET Core process, and that is the same or true for Windows and Linux. So it's exactly the same. The file name may be different, but it is the same process. So if you want to make it a little bit more concrete, let's look at the exact steps the core CLR takes in order to load a .NET profiler into the process. And so the first thing it does, it looks for environment variables to see whether there's actually a need for a profiler. And so I'm not showing this environment variable here, we'll see that a bit later, but basically it says, do I want any profiler at all? So if the value of that variable is 0, then no profiler will be loaded. So assuming that this variable is 1, so it means I want to have a profiler into this process, then core CLR looks for this environment variable to find the path to the DLL that is implemented, or the SO file in Linux that implements the appropriate COM class. And so this is for 64-bit. You can probably guess that if you have a 32-bit process for whatever reason, then that would be with a 32 suffix. And then once the DLL is found, it is loaded into the process. And then to create the actual class, the actual object, which is the COM class implementation, there's another call that is made to DLL get class object, which is a function that must be exported from the DLL. And so if you have any familiarity with COM on Windows, you may know this function. That's the same function any COM DLL must export. Otherwise, it's not a COM DLL. It's maybe just some other random DLL, but it's not a COM DLL. And so this function must be exported, and the CLR just looks for it and then calls it and asks for a particular class ID. Now, in the world of COM, everything is named using a GUID. A GUID, which is just a very long number. There are no strings there, they're just GUIDs. And so you have to tell the CLR what's the GUID of your profiler. This is done with another environment variable called core CLR profiler. And so the CLR reads that environment variable and then calls DLL get class object with that particular class ID. So assuming that actually exists, and DLL get class object returns something called the class factory. Again, this is something from the days of COM, which of course still exist, fortunately or unfortunately, depending on your perspective. And so what the CLR does, it gets back something called the class factory. A class factory is like a normal factory, which is something used to create other objects. And so the class that should be returned from that call is a class implementing the iClass factory interface. And now the CLR gets to the final call as far as the DLL is concerned, at least. It's calling create instance. That create instance should create the actual profiler object, returning an interface pointer to the core CLR. And now the core CLR just calls a method called initialize on the profiler. So I mentioned earlier COM. So what is really COM? Now, we're not talking here about the full COM implementation in Windows. That has its complications, and that's not the case here. COM really has only two very fundamental concepts. And the first of them, which is used, is just the idea of programming against interfaces rather than concrete classes. So an interface, we know that from almost any programming language you can think of, is just a contract, abstract contract that must be implemented by something that adheres to that interface. And so the profiler implements an interface which is then just called by the core CLR with the initialize method. And that's the final step where the profiler is ready to go. And from that point on, the profiler will start getting notifications using the same interface, core profiler callback, and more derived interfaces about everything that's going on in the process. And in fact, the profiler can select what kind of notifications it wants to get. And so, if you are familiar with COM, how many people are familiar with COM in Windows? Right, so quite a few. How many like COM? Oh, there's one guy. Well, two guys. All right, that's much more than I expected, like an infinity% more. And so, if you're looking at classic COM, you know that to create a COM object, you need to call the co-create instance function on Windows. Now, co-create instance is not used by a profiler. And there are several reasons for that. One of them is that co-create instance uses the registry by default. And of course, registry is a Windows thing. It doesn't exist on Linux, on Mac. And so it wouldn't be a good idea to kind of rely on the registry because it doesn't exist. And worse, something which is a little more subtle, is that if you want to call co-create instance, you first have to call a function called co-initialize EX, to make the thread enter an apartment or have a threading model. And that's a problem in the case of a profiler because it means that the client application may already entered a specific apartment, so you can't really change that. And so the profiler, or sorry, the core CLR doesn't call co-create instance. It simply can't work, but it does something very similar as an equivalent. So it actually loads DLL explicitly, calls DLL get class object, gets back the class factory, and then calls create instance, the thing I showed you in the previous slide. And so this is like simulating COM, but not exactly. There's no part in the registry here and no setting of any threading model because that typically may already been set by the client and you can't really change a threading model of a particular thread. And so that wouldn't be a good idea. So the problem here is that all this stuff is great, and COM exists on Windows, and everybody is happy or not. But what about Linux? What about Mac? They don't have anything like COM. So Microsoft had to create something that allows it to simulate a lot of stuff in the COM world that don't exist on other platforms. And they create something called the Platform Adaptation Layer, or PAL. So this PAL stuff is a library that implements a lot of COM concepts in C++ so that we can use them when we're writing a profiler. So for example, there are some simple stuff like the definition of unknown. So definition of unknown, we need to have that on Linux as well. There's no default header file on Linux that has these things, so we need to provide that. And so the PAL is currently bundled with the core CLR source code itself. So you need that. And so you need to just copy a folder with some files there to your own project, and then just have the proper settings in the project properties so that the include that you have will search in those directories. And so currently, it's not a separate component. I think it should be. But it is bundled with the core CLR, so I have to actually get the core CLR from GitHub and then just take those particular libraries which are a particular folder which implements the PAL. And that makes my life a lot easier. Now what about the project itself? How do I build for Windows and Linux with the same code base? And so the core CLR itself, the source code itself, uses the CMake build system to make the build work. And CMake is a hierarchical nature, so you have a CMake, and then you can have more CMakes in subdirectories and stuff like that. So Visual Studio today has some support for CMake, but I don't think it's good enough yet. And so I started going to the CMake way, but then I found out it's just too complex to get things building correctly. And so I decided to go back to MS Build. And that, I think, is a good decision because Microsoft already supports building for Linux, so that's not a problem. You can build executables with Visual Studio that run on Linux. And so why shouldn't I just use that? So the way I use that is by using a shared items project. Now, a shared items project is not as common as it used to be. It was created in the Windows 8 and Phone 8 days to share code between those platforms, but it's still available in Visual Studio and actually very useful in this case because all my source code in that shared folder or shared project items, and then I have two separate projects, one for Windows, one for Linux, which have the proper settings for the compiler and linker and just add reference to that shared items project. And so I get to build these two things at the same time using the same source code base, and this is one thing I want to do. So what kind of compiler can I use for Linux? And so we have GCC, which is a common compiler on Linux, and there's Clang. And Clang is actually a better choice in this case because it supports some Microsoft extensions. So if you're familiar with UAD off and stuff like that, decal spec, all these things are supported by Clang but not GCC. And so I want to use Clang. So where do I get this Clang anyway? How do I test these things? I mean, I can test on Windows. That's fairly simple. I'll show you how to do that very soon. But how do I do that on Linux? So I need to set a bunch of environment variables, those variables that the core CLR reads and then acts upon, knows which profiler to load and all that stuff, which we'll see. And then we can launch an application using those environment variables that are now in effect. And so the profiler will load up. So in Windows, fairly simple. What about Linux? So one way is just to deploy and test that on a real Linux or Linux virtual machine running on Windows. And I'm assuming you want to build with Visual Studio on Windows, of course. But there's another way which is better and easier, which is using the Windows subsystem for Linux, a feature that is available in Windows 10, starting with version 16.07 and later, which is fairly old by now, the anniversary update. How many of you have heard of WSL? So quite a few of you. So the idea here is that we have actually a Linux we can install on Windows. So current version of WSL is known now as WSL1 because WSL2 is in the works and already is available using the insider preview builds if you are using those. But WSL1 is fine for our purposes, and this is a true Linux. So when you want to install that, you go first to the Windows features, you turn it on, and then you can go to the Windows Store and download your distribution of choice. It can be Ubuntu, Debian, and maybe Kali Linux, whatever you fancy. There are several distributions available. And then you can install .NET Core on that WSL installation just like any other Linux. So you go to the website where you install .NET Core and just follow the same instructions for Linux on your WSL installation. And so this is the same machine. It's sharing the same file system, so it's much easier to use. And on that WSL, you also install the compiler, the Clang compiler. Again, in exactly the same way as you would install that on a normal Linux. And then you can point Visual Studio to that compiler and say, hey, use that compiler, use WSL compiler to build the application. And so we can also test that using WSL, setting the same environment variables and then launching our application using a shell that has these variables. And it's simply easier and faster if I want to do lots of testing and going back to the code and fixing and testing again. It's going to be much faster than working with a true Linux virtual machine or even a physical machine. So this is the theory, and these are the variables we're going to use in order to make a profiler work. So the first variable, this is the one I didn't mention yet, is the core CLR enable profiling equals 1. This is the one that's saying, hey, I want a profiler. If that variable is not set to 1, then the rest of the variables are useless and will not do anything. And now we have a profiler, then we have to specify the GUID for the profiler. This is necessary because the core CLR will call DLL get class object to ask for the class factory using this class ID, this GUID. So we have to provide that, and we have to provide the path to the DLL or SO object. Why? SO file, because there is no registry now. We have to know where that core CLR has to know where to find that module. There's no registry that maps GUID to a path to load. And so this is the part where theory actually ends, and we want to look at some code. I mean, I promise will be some C++ here. So let me show you what that looks like. So again, I won't be doing live coding, and you'll see why in a moment. So here are my three main projects. I have a DotNext Profiler shared project. This is my shared items project. This is the one hosting all my source code. And so I have here several files. The first one is this one called dllmain.cpp. And this one holds the entry points into our DLL. Now I'm saying DLL, but of course I mean DLL in the Windows and in the Linux sense. So I'm calling that DLL as a generic term. So if you've ever written a native DLL, you may know that DLL has a DLL main function, or can have one, which is called in several scenarios. For example, when the DLL is loaded into a process, and when the DLL is unloaded from a process. So this is a very Windows thing, but because of the PAL, that platform adaptation layer, it is now a Linux thing as well when building a profiler. So I'm writing code which looks like pure Windows, but it is understandable, and it's working with the core CLR on Linux as well because of that platform adaptation layer. And so when the DLL main runs here with the process attach argument here, then it means the DLL currently is loaded the first time into the process, so the profile is now loaded, and I can just log this information here using a logger that I've written for this purpose. And conversely, when the DLL is unloaded, typically when the application shuts down, then DLL process detach is going to be called, and then we'll just log the fact that we're shutting down using that particular logger. And so the first thing that happens, as I mentioned, the DLL is loaded, DLL main is called automatically, and then the function DLL get class object is called. So here's DLL get class object. This function is exported. So it's exported and normally using this extern C. That's enough on Linux. On Windows, we have to actually add a module definition file to just export that particular function. That's actually the only file that is different between the Windows and the Linux implementation. And here we can see that we get the parameter of the class ID that is requested by core CLR. So this class ID, of course, comes from the environment variable that I mentioned earlier, core CLR profiler. And so the core CLR says, hey, this should be the class ID, let me ask for it. And so what I need to do here is see whether that's actually the class ID that I support. So here's my class ID. This is the class ID I generated. So I just generated using the normal GUID gen tool. That just generated something random for me, and that's fine, just committed to that. And that would be the value I have to set to that environment variable so my profiler has a chance of loading. And then when the core CLR asks for a class factory for this one, I have a class factory that I've built. I'll show you that in a moment. And then just go ahead and return that to my client, which is in this case the core CLR itself. So let me stay back a bit and look at the properties of these projects. So here's the properties of the Windows project. So the Windows project is just a normal DLL. There's nothing special about it. I created that as a sort of an empty DLL and then started adding the code. So there's nothing special here, too much. But we can see here some definitions that we have to provide from the compiler's perspective that are used by the PAL. That adaptation layer looks for some variables during compilation to make certain decisions, such as that bit 64 constant that says this is a 64-bit process rather than a 32-bit process. For language, I can use C++ 17. That's the best thing to go right now. This is the supported version currently in Visual Studio. Also for Clang, it supports the same thing. And so this looks like sort of normal Windows DLL. The more interesting part, perhaps, is the Linux project. So here's my Linux project. And by the way, of course, both of them referencing that shared project. So both of them just referencing the same thing. And the only thing to make right is those properties of the compiler linker to make things work properly. So you can see here in the General tab, here's the platform toolset. That's Clang for Windows Subsystem for Linux. And so I've installed WSL on my machine, and then installed Clang on WSL, and then I'm just pointing that using Visual Studio, and just invokes that compiler on WSL automatically for me. So this is actually one of the supported options here when trying to compile for Linux. So you can use some remote Linux machine, like a VM or a physical machine even. You can use GCC, but as I mentioned, GCC is not a good option for compiling a profiler because it doesn't support the Microsoft extensions. And so you can see in the command line here that I have to add this thing. This flag says MS extensions, and this is required so that stuff like declaration specifier and all these things that are Microsoft specific will be understood and compiled correctly by Linux. So these are kind of the main thing I have to do to make things sure everything works. And for Linux, I have to point here using the additional and include directories to that PAL that I mentioned, those directories that I copy directly from the core CLR source code to my project hierarchy and just point that there, because that would make everything sort of compile. And so that's from a perspective of settings. Now, in my common node here, there's actually a file called common.h where I try to include everything that I need from Windows and Linux perspective, so everything kind of works appropriately. So for instance, one of the things that we have on Windows when working with COM is the idea of a smart pointer. So a smart pointer knows how to do add ref and release properly so that I'm not leaking any objects and not destroying object prematurely. And so in Windows, you may be familiar with the active template library, which has a class called ccom pointer that allows you to manage such interface pointers. Now, Linux doesn't have them, but the PAL provides them. And so if I'm on Windows, I'm just including ATL base, which is the normal LTL header that has definitions for ccom pointer. But if I'm not, then I have to do something else. I'm including ATL.h, which is a PAL header that has the equivalent definitions for various ATL constructs such as ccom pointer. And by the way, ccom QI pointer, for instance, if you're familiar with that, is not implemented by the PAL. So I'm not going to use that unless I want to implement that myself, because it will not compile on my Linux compilation here. And so, of course, I'm doing some general stuff, such as declaring a logger. So I have a verbosity level, I have a class called logger and stuff like that. And the only thing we need to really make sure is that we're using some things that are supported on Windows and Linux. So how do we do that? We try to use as much as we can the C++ standard library, because the standard library sort of provides and promises compatibility on the source code level. And anything that is not exactly the same, we can abstract away by providing some class that would provide the abstraction over the actual implementation. I'll show you an example in a moment. But maybe before we continue with the code, let's just demo it. Maybe it doesn't really work. And so here I'm opening a command window first for Windows. Then we want to test that on Linux as well. And so what I've done here, I created two scripts that just set those environment variables to the correct values. One of them is a batch file for Windows, and the other is a bash file for Linux. That's much more scary. But again, depending on your perspective, some people are used to Linux, I'm not. And so what I'm doing here, I'm going to go to the directory where my output is. So I'm going to just paste it in. And then I'm going to run the batch file to set up those environment variables. Then I can use the set command just to make sure that, in fact, I have these variables set up correctly. So here they are. So I can see they're pointing to the right location. At least I have to make sure. So I have the correct GUID here. That's the GUID I defined in my source code, and I compare to that parameter in my DLL get class object function. So now anything I'm running from this console window will have these variables set up, and so my profiler should load up automatically. So now I'll go to a few samples that I created here. And so one of them is an application that is in .NET Core 3, which is an adaptation of my Mandelbrot set, which I like very much. So I can run that as an executable or run it using .NET with the DLL. That's essentially the same thing. And here's my Mandelbrot application. I can go ahead and zoom in, and this is a fun application to use. And what happens is that all the events that I've registered for have actually been written to a log file. And so when I shut this down, I should be able to look at that log file. And one of the things I added here is that the log file, the logger itself, looks at this environment variable to know where to put that particular log file. So it's in my ctemp directory. So here's my ctemp. You can see there are a bunch of log files here already. So this is the latest one, which is created right now. And we can see some stuff here that we've actually been recorded as part of running my application. So for purposes of making this data a bit easier to use or to look at, I created a logger that can show you this stuff in kind of a bit easier way. So you can see the actual time it was recorded. So that's about 6 p.m., which is, I guess, kind of correct. So just to prove I'm not making this up and it's a log file I created maybe a week ago, maybe I did something to make you think that it's right now, but it is really happened right now. And we can see stuff like here's the get class object was called here. Here's the initialize method, which I haven't looked at yet. And then we can see stuff like threads being created and assemblies being loaded, types being loaded, and maybe even if I continue looking, let's say I have a find thing here. So maybe I'll see a JIT compilation starting. So you can see that there's something that started JIT compilation and finished here. So we can actually, if you want, we can measure times. We can also look for other events such as garbage collection. So we can find here there's a garbage collection started here. We can see this is a Gen 0 collection that started here and finished here. So we can get some timings, and in fact we can get some even more information from the CLR asking what references survived, what references have moved, and all kind of internal information that can help us understand or diagnose issues, such as references that never go away. So we have something called a memory leak. And so memory leaks are not really possible in .NET if you're using pure .NET because it's not a leak, it's a bug. That means you have some memory, some object that doesn't go away. Why? Because you're still holding a reference to it. The problem is that you don't think you're holding reference to it, and that's why that object doesn't go away. So it's not technically a leak because you're at fault. But you want to understand who is keeping that object alive. And so you can get from the CLR at any point in time, for example, a list of all the GC roots. And if you know something about the garbage collector, it works with roots as the basis of traversal for identifying live or dead objects. And so for the purpose of this demonstration, I just logged things out. And of course, in a more realistic profiler, you'll do some more analysis on that information. So that was an example on Windows. How would it look like on Linux? And so I'm going to run WSL. WSL is a command line. You can use bash as well, which just opens up a command window, which is now Linux. Look at this. I can type ls. So how cool is that? I mean, really? And I'm going to do exactly the same thing. And so I'm going to go to my script here. So first I'm going to move to that directory where the actual profiler is, and I'm using copy-paste because, as you know, in Linux, it's very easy to make mistakes because of case, and I hate that thing. And so I'm going to use the set profile, this time the bash script, to do essentially the same thing, to run this, so that it's available for my shell, my current shell. I can also make sure using print env So I can print the environment variables and see that here's my core CLR profiler again, and the profiler path this time. Notice we have a Linux path here because the normal drives are mounted under /mnt, so this is where I pointed to, and we have, of course, the most important flag that enables profiling. So now I'm going to, again, go to my applications or demos that I created. And this time I have actually installed .NET Core 2.2 on my Linux, not .NET Core 3, but it doesn't really matter. So I'm going to go to, let me copy that and move to that directory. And then, okay, sorry, this is the Windows directory that definitely won't work. And so let's go to my application directory, the real application directory. And now I can run whatever I want. So in this case, I have two applications here. One of them is very simple. It's called the primes counter. It just counts some primes. So I have this as a DLL built with .NET Core, and I can just run it. And it just shows me a bunch of prime numbers between 3 and 100, so not something very complex. But again, I can go ahead and open the log using the viewer or just a text file. This is a new log. You can see it's much smaller because it's a very small application. And this time, it's completely, everything is a Linux here in a sense. So it may not be easy to tell that because it is eventually .NET. And so there's a profile DLL loaded, and there's initialize call, and types are loaded, and stuff is happening. JIT compilation starts and finishes, all these things. So it looks kind of the same, and of course that's a good thing. And by the way, notice that the process ID here, this is maybe the only clue, is 29. Now, if you know Windows, process IDs must be multiples of 4. So 29 is never a process ID which is valid on Windows. So this is kind of maybe a small proof that it is in fact Linux running this. And in fact, we can of course go to Process Explorer or other tools and see that this is running as a Linux process. This is running as something known as a Pico process. A Pico process is the way WSL is implemented on Windows. So we can take something a little bit more challenging. So I've created a web application, just a normal .NET Core web application, just running the wizard, so to speak. And so I can run that as well. So it's called the Simple Web, .dll again. And now the Kestrel web server and all that stuff that's behind the covers in the ASP.NET Core is running. And it's listening on port 5000 here. So I can go ahead and go to a browser and just go to a localhost 5000. And here's my application. So I can navigate the application. Here's the privacy policy. I can try to, let's say, log in, for instance. And because I haven't really connected that to any database, then I'm going to get an exception, for instance. And that's all fine and well. The application even reports that using the console. But again, this is something I actually recorded this using the profiler. So I can go back to my log, and this is a new log right now, which was just created at this point, and this is about my new web application. And so you can see the process ID is completely different. It's a different process, and this is the web application itself. You can see there's ASP.NET Core, something that is being created there. We can even find the exception if we look closer. So here's the exception, that's the exception loaded, that's not the one. So you can see here there's an exception that is thrown at that point. In fact, at that point, I can ask the CLR, give me a stack snapshot, or give me the call stack of that exception. So I can log that as well. I haven't done that, but it's something you can do at that point when you get the report of an exception. And so this is running on Linux. This is a true Linux application to run the same way on a real Linux machine. So from a developer's perspective of writing code and testing and things like that, it's really easy to work with WSL, and I really like this experience. So now let's go back to the code. So I want to walk you again through the phases for just launching the profiler and telling the CLR what I want to happen. And so as I mentioned, we started with with DLL main. So in DLL main, we have this core profiler factory class. This is the class that implements the class factory. And then again, what I said earlier about com holds true. This is just a class implementing a bunch of interfaces. So here's the class. It just inherits from an interface called iClassFactory, and all interfaces in the com world inherit from the IUnknown interface. And so we have these three methods that are always there. That's query interface, add ref, and release. And there are these two special methods that are special to iClassFactory. In this case, only one method really matters, which is create instance. So this is the method that the core CLR will call to create the actual instance of the profiler. So you can see here what I'm doing here. I'm just using the new operator in C++, creating a core profiler class. This is the class implementing the actual profiler, which we'll look at in a moment. This is the most important class. The class factory is just a way to get an instance of the class factory loaded. And if anything goes wrong, I can report that by returning an appropriate H result, which is the classic status or error type in the com world. And once everything is okay, I'm just returning the interface the client expects. Again, the client here is the core CLR. I'm the server, I'm providing some functionality, and the core CLR is the client for me. And so the most important class is really core profiler. So core profiler implements one of those interfaces that are defined by the profiling API. Now, these interfaces are the same as the interfaces defined for the profiling API in the regular .NET framework. So if you've ever done a profiler using .NET framework, this is essentially the same thing. These are exactly the same interfaces. So the interface here, it started with iCore profiler callback, and there is iCore profiler callbacks 2 and 3 and 4 and 5, and as you might imagine, each interface extends the previous interface to provide more options for callbacks, more things that I can implement. And if you look at the interface, you see that it's long, and I mean, it's really, really long. I mean, there are many methods. So fortunately, you don't really have to implement all of them. In fact, you have to implement very few of them if you want. All the rest you can just return SOK and be done with it. You just need to implement the things that you actually are interested in. And so let's see how that is implemented. First, in the com world, you have to maintain a reference count. So to maintain a reference count, you need to manipulate that value using add, ref, and release appropriately. So in my class, I have something to store that reference count, which is std atomic. So std atomic is a C++ 11 class that knows how to work with atomic types. So if I want to increment a reference, technically this could be done from multiple threads at the same time. I don't want to lose any count, so I need to use something which is thread safe. And so if you're familiar with Windows, there's a function called interrupt increment in the Windows API to use that, which in fact is an intrinsic. It's actually an instruction to the processor. But the problem is that in Linux, there is no such function. Or there is such a function, but just called differently. And so you can't really use that unless you start writing conditional compilated code. And you want to avoid that if you can. And so the best approach would be to use the C++ standard library if you can, if that thing you want to do is actually supported. So fortunately, starting with C++ 11, this is supported. So I can use std atomic and then just use that ref count with ++ and -— operators, which behind the covers call the appropriate intrinsic on the particular processor. So I don't have to worry about that. I let the compiler deal with that, with those differences. And so this is about reference counting. Now, for query interface is the function that says, hey, I want a different interface. Do you support that? So query interface expects two parameters. The GUID of the interface, remember everything in COM is identified by an interface, by a GUID. including interfaces, and a pointer for the result. So what am I supporting? I'm supporting INON, which I must, and then all the other interfaces that I inherit from. So I have to support this, and if one of them is requested by the CLR, I just add reference and return a proper pointer to myself with some casting so that the pointer is adjusted if needed. In this case, it's not, but we're using static cast anyway. And again, if you're not too strong in C++, you can disregard these tiny details. That it's more important to understand the concepts, and then you can later dig into the details. The code, of course, will be available for you, and I'll show you the link afterwards. And so my addref and release implementation is really simple. Addref just does ++. This is not a normal ++. It's a thread safe ++. Why? Because it works on the atomic variable. And so the implementation is different behind the covers, but it's easy to use. Release is very similar. I'm going to do a -, and if the value is 0, after decrementing, then the object no longer needs to exist. And so here's the place where I use delete this, which is sort of the suicide operation in C++, because nobody's using that object anymore, and so I have to kill the object. And so these are sort of the basic management tasks of every COM class. I think it's not too bad. You can just copy-paste that to any COM class that you're using. And then the most important method that you need to implement, you must implement that in your profiler, is called initialize. This is the call that is made by the core CLR telling you, okay, here's your initialize method, and I'm calling you with a pointer to myself. So the CLR hands a pointer to the profiler, so you can have a bidirectional communication. So on the one hand, the core CLR is going to call me on my implementation of all these iCore profiler callback interfaces. On the other hand, if I want to tell the CLR something or ask the CLR something, I need something to work with. And that's the INON pointer I get here, which in fact is of a type which is much more specialized. And this is the type iCore profiler info 8. So remember, my profiler implements the callback interfaces, but I have just an info interface to talk back to the CLR. And of course, you don't have to use the latest version. You can use 7, you can use 4. It doesn't really matter depending on what kind of information you need to get from the CLR. But you need to store this value. So I'm storing that value in my _info member to be used later. So in the initialize method, I have to do two things. The first thing is to store the pointer that I get, so I can query the CLR later. And the second thing is to tell the CLR what events I'm interested in, because the CLR has a long list of events or categories of events it can call back to me, but not everything may be interesting for me. And of course, in a real profiler, this is configurable. You can say, hey, I'm interested in allocations. I'm not interested in threads, or the other way around. I'm interested in that and in this. And so we need to tell the CLR what we are interested in. So in this example, I'm interested in module loads, assembly loads, GC events, class loads, threads, exception, and JIT compilations. And of course, the list is, again, longer. So I can just press F12 and see the entire list. And of course, there's documentation that specifies what each of these values actually means. And so I have to specify what I want. Without that set event must call, I'm going to get 0 notifications from the CLR, which means my profiler is completely useless. So once this is done, this is the point where, from the core CLR's perspective, the profiler should be ready for anything. And so now all I need to do is just wait for these callbacks or call back to the CLR. So just as an example, when assembly load finishes, I'm getting a callback here, and this is why I got this information into the logger. So what I'm doing here, I'm calling back to the CLR and say, hey, I got an assembly ID, which is some form of number. I have no idea what to do with that, but the CLR does. So I'm asking the CLR, get assembly info. Here's that assembly ID. One of the things I get back is the name of the assembly, and which module this is actually implemented, and even which app domain it is in. So in .NET Core, we don't have app domains, so this parameter is useless. But again, the same interface is here because that's the way it was, and it still is, in the classic .NET framework. So the interface remains the same, although maybe some parameters may now be useless because they simply are not supported. And so I get back the name, and then I put that into my logger. If we take a more complex example, so here's a class load finished. It means a class is completely loaded, its static constructor has been called, if any, and I want to know about that, for instance. So I'm going to get back the call that class load finished. And again, what I get here is various IDs, which are some kinds of integers or pointers which are opaque to me. I don't exactly know what they're actually holding, and that's fine because I can find out anything that I need by talking back to the CLR. So I have the same underscore info here, which is just, again, I just remind you, this is the pointer to iCore profiler info something, and with that I can get information on the class itself, and then, for example, get the type name of that particular class, which is used here in the helper function that I created because I needed that in many locations in my code. So I created a simple wrapper that just goes ahead and finds the name of a type. And it turns out it's not that easy. And so if you're thinking about getting that information, it's really about doing reflection. But of course, you can't use .NET code in this scenario. You have to use C++ code. And so you have to talk to the CLR again and say, hey, I want the metadata for this particular model. And what you get back is another COM interface, the metadata import, which has something called get type dev props. In fact, it has a bunch of methods for enumerating types and interfaces and members and methods. Everything you can think of is there. In fact, these are the real APIs that are used by the CLR itself. And so we're used to using reflection using the types in .NET, but really this is the real deal. This is happening underneath. And now I have to actually use it. And so again, this is all documented because this is the same approach used in the classic profilers in the .NET framework world. So we have to do some stuff here. Now I want to discuss some of the challenges of writing this kind of code. And so this class looks very simple in the sense that I'm talking to the CLR and using types that are coming from Windows. Because of the platform adaptation layer, they also work on Linux and are being compiled and everything is just fine. But in some cases, it's not that easy and we have to do things about that. So for instance, I have my logger here, and the thing is that if you try to log behind the scenes, what I have is a file, and I'm using here the very simple OFStream class from the C++ standard library again. I want to leverage what I can from the standard libraries, so I don't have to write conditional compilation and try to kind of see how that would work on Linux and how that would work in Windows and so on. So I'm trying to minimize the changes in the source code. Of course, you can use other libraries such as Boost libraries, which are also cross-platform. You'll have to be careful, but you can technically use them because they abstract away the differences of the platforms. So in this case, when you have a logger, you may be calling that logger, which is the file behind the covers, by multiple threads. Again, you need to synchronize that. So how would you do that? So let's say I want to synchronize in Windows differently than on Linux for whatever reason. There is a class stdmutex which you can technically use that should work in both ways. But let's say I want to do things differently. And so I created a class here called mutex with a capital M, which abstract that functionality. So I have a lock function here and an unlock function here. And from the header file only, you cannot see the implementation. What you can see here is there's a struct called impel, and there's a unique pointer, which is essentially a pointer to something that is automatically destroyed when the object goes out of scope. And if you look at that impel thing, it's not defined here anywhere. But the compiler is perfectly fine with compiling that. That's because what I'm holding here is really a pointer. And a pointer has the same size no matter what you point to. And so the compiler says, hey, that's a pointer. Because you're not using that pointer in an explicit way in this code, in this particular header, that's fine. I know what the size of the mutex object should be, just the size of that pointer. And so the implementation is hidden in the CPP file. So in the CPP file, I decided for the mutex implementation, the kind of internal class here, the nested class, something that is also exists in C#, I can actually create this class and I want to use a critical section on Windows. But on Linux, I want to use the classic mutex header, which is part of the C++ standard library. This is just an example, of course. And so this is a pattern, or maybe an idiom in C++ called pimple, which is short for pointer to implementation. So what we have here is just a pointer to the implementation, but it's not defined here anywhere. And so the layout of this structure is actually hidden in the implementation, and clients don't need to know how to use it. So this is a very, I think, elegant way of hiding the implementation details when you have something that is different on Windows than on Linux. So this is one way of doing that. And so in most cases, what I want to do is use classes that are part of the standard library, of course. I don't want to use these tricks unless I have to, but sometimes I have to. There's really no other way to do that. And so most of the work that a profiler does is implementing these various methods for everything that can happen in a .NET process. One of the most interesting things is that when a method is JIT compiled. So when it's JIT compiled, you can get notification on that, and then what you can do is insert your own IL into the method. So when the method starts, the method exits, you can add your own code. So I'm not going to show you how to do that because we don't really have time for that, but it's not different really than the way it was done in the classic .NET framework. So this is how you can actually instrument every method, or maybe some part of the methods that you're interested in, and add your own code as part of the code generated by the JIT compiler, because you get these events for JIT. In some cases, there are events for read-JIT in the method. Again, you can insert your own code in there. I'm not saying it's easy, but it can be done. You need to know some IL to do that. But there are examples, and I'll give you links afterwards to where you can find more information about that. And so this gives you really the ultimate power. You can see here stuff like references that have been moved, surviving references after garbage collection. Everything you could ever possibly want to know about the .NET process is hiding in here. Some of that information is available with other tools. Some of that information is not. And in any case, you are in control because you can tell the CLR to do things, something you can't usually do from the outside. So again, this is for really all those difficult cases, or in case you want to write your own tools to do some specific analysis of a particular scenario. A .NET profiler is not easy to build, but as you can see, the skeletal structure is not too complex. Once you have this in place, you just start to implement the methods you're interested in, and then getting out the information that you require. Maybe even talking back to the CLR and instructing it to do stuff. So let me just summarize that a little bit. So .NET is cross-platform, and that's why these PAL and things had to be invented by Microsoft. Now, currently, it looks like sort of an afterthought. The idea of profiling is not yet, I think, dealt with seriously by Microsoft. That's why I have to sort of copy code from the core CLR to my project. This is ridiculous. It should be some kind of NuGet package I can just add a reference to and just use that, and that's it. And the only examples Microsoft provides for .NET Core Profiler is dated something like 3 years ago. And so it's pretty clear they're not focusing their energy on that, at least not at this time. Hopefully that will change. So here's some links for you. So first, these demos that I've shown you right now, and the presentation itself is available in the first link. And then you have some other links which are easy to click once you look at the PDF that is also available there. And so one of them is the CLR profiler samples I mentioned, which are pretty old but still work in some sense. There's the blog from David Broman, which used to work on the profiling API at Microsoft. So he stopped blogging, it kind of moved to other stuff in 2013, but its blog is probably the best there is discussing all the intricacies or re-jitting or jitting and how to load and how to get information, all that stuff. So his blog is still available, and it's a good read if you really want to dig deep into the profiling API. And finally, there's the old CLR profiler for the classic .NET framework, which is not maintained anymore, but still a good reference of how to talk to the CLR, how to implement methods there, how to insert your own IL into JITted methods, and things like that. So with that, I want to thank you for your time. And if you have any question, you can catch me later on the discussion zone.
Yeah,
thank you.
That's true. Thank you.